Good morning. We stopped at discussing the achromatic doublet. So, in this chapter, we are discussing various types of aberrations that could be there in any optical system. To begin with, we discussed the polychromatic aberration, and as you may recall, if you have not watched lecture 13 and lecture 12 yet, please go ahead and do that. Polychromatic aberration arises from the fact that each wavelength has a different refractive index, or it feels its velocity changes differently inside each medium, and so they focus at different points through a lens. And so that's where we saw how we can use something called an achromatic doublet. We also solved a problem on achromatic doublet using crown glass and flint glass. We derived the equation omega by f plus omega prime by f prime is equal to 0, where here omega is refractive index for blue minus refractive index for red divided by the average refractive index minus 1. And similarly, omega prime is ND prime minus NR prime and average prime minus 1. So essentially, to remove the aberration coming from polychromatism, that is, if I have a lens, right, blue and red light, they have different refractive index. So you would have, for example, a set of red rays coming would focus here, and similarly a set of another type of rays, another color, may not focus at the exact same point because the refractive index is different, and this difference in focus is what causes the polychromatic aberration. And to get rid of that, we saw that you can have an achromatic doublet, that is, instead of having just this one lens, you could have another lens that is attached. This is the extra lens that we are adding. For example, if this lens is made up of crown glass, you can have this lens that is made up of flint glass, and this omega and omega prime are properties of these lenses, which come from the refractive index of blue and red that are dependent on the material. Recall that the refractive index is dependent on the material, and for each material the refractive index of red is different from refractive index of blue. So by adding two lenses, we have seen that we can remove polychromatic aberration. We have also worked out an example on this one. So if you have not seen that, it's in lecture 13. Please go ahead and do watch that. And today what I would like to discuss is monochromatic aberration. So if you have monochromatic aberration, that is, we have only, say, one type of line, that one wavelength, just red color or just blue color. So we are not looking at the changes in refractive index as a function of the wavelength of light. We are truly looking at aberration coming from one single type, one single color. So if I have, say, a lens, so far we have been doing what is called paraxial optics, right, or Gaussian optics. That means we have been limiting ourselves to rays that are around the axis. So that means if I have a lens like this, I've been limiting myself to rays that are close to the axis. So these rays go through the lens and they get focused, right? And this is the focal point. So we'll call this focal point as the paraxial focal point. So this is the paraxial focal point. But if you consider the marginal rays are rays that are coming at a higher elevation. So now there could be rays that are going here, right? And these rays would not necessarily focus at the same point as the paraxial focus because they're coming from a different height, so they would bend differently, right? So they would go something like that. So you see, this is the focus, and this focus is what we call as FM, right? This is the marginal focus. Once again, here we are only looking at one single color of light. That's why it's a monochromatic aberration. So even if you have a single color of light, the rays that are coming from the paraxial region focus at FP, the paraxial focal point, whereas the marginal rays focus at a different point, that is the marginal focus. That is because there is a difference in the height, right? So we can see that there is a distance between these two. So I can define the difference between FP minus FM as what we call as longitudinal spherical aberration. So in other words, longitudinal spherical aberration arises even for monochromatic radiation because the marginal rays do not focus at the same point as the paraxial rays, right? So your image that you see would be a mixture of these two focal points, right? So you would see that your image is not sharp, that is, your image is not focused. That's because there is no one focal point. All the rays that are coming from marginal rays have a different focal point compared to the paraxial rays. And because they don't have a single focal point, you would see that the image is not strictly focused, right? So now if I were to put a screen here, if I put a screen here to see the image, so this is our screen. So the marginal rays are going to go here, that way, right? So then I can call this height, right? So we're placing the screen at paraxial focus at FP, right? And the height at which the marginal rays are incident on this screen placed at the paraxial focal point, that height is the lateral spherical aberration, right? So we have spherical aberration coming from monochromatic light, and then we can decouple it into two things. One is longitudinal. There is a difference between paraxial focus and the marginal focus, and the lateral spherical aberration, that is the height at which the marginal rays are on the screen placed at the paraxial focal point, right? So in general, if you were to look at the image anywhere here in between the marginal and the paraxial focal point, anywhere in between here, right, it would appear like a circle, right? And there is a sweet spot between this FP minus FM, between the focal length of the marginal focus and the paraxial focus, where the image would appear to be distorted the least. And at that point, we say we have a circle of least confusion. Once again, because the focal point for marginal and paraxial rays is different, you see that the image is sort of blurred or extended, but somewhere in between the marginal focal point and the paraxial focal point, you would have, if you go between that, there would be a place where you are achieving best of both worlds in a way, and so you would have an image with what we call as the circle of least confusion. So now what we will try to do is we will try to derive an expression for what the spherical aberration is. But before we do that, I would like to note that deriving the expression for spherical aberration is very complex process. So first what we will do is we will do refraction at a plane surface and see how we can use the results from that and extend them to a spherical aberration case. So let's do that. So if I have a plane surface, right, a plane refracting surface, let me change to red color here. So say I have this surface, right? This is the medium with refractive index N2, and on the other side I just have air or vacuum with let's say, or in general we have N1, right? And let's draw an optical axis here, and we're going to call this as the z-axis, right? So if I have an object at here at point P, let's call this distance as z0. Recall our sign convention, anything that is to the left is negative, right? So we have a negative z0 here. So a ray of light going from this point P, say at an angle alpha, right, is going to get refracted into the medium N2. So it is going to get refracted. It's not going to be at alpha. This would be at an angle beta, let's say. Right. That is the refraction, and we know how to relate alpha and beta. We know that alpha and beta are related by the Snell's law. N1 sine alpha is equal to N2 sine beta. We are just looking at simple refraction of a single ray coming from a point object P going into a medium from N1 to N2, and the interface is placed exactly at z is equal to 0, right? So now if I want to look at the image of this point P from, if I'm standing inside this, if I'm just looking at this ray, the blue color ray that is refracted, it would appear as if it is coming from here where the angle is beta, right? This is because the original ray which was going from point P at an angle alpha refracted, and inside surface N2 it is at an angle beta, right? So if you were to extend this line, the refracted line, this line, straight back to medium N1, right? If I just draw a straight line, that would also make angle beta, right? So your image, the virtual image, would appear as if it is coming from this point. Let's call it Q, and let's say the distance of Q from this is z1, and obviously because it is to the left, we have to give it a negative sign, right? So if this is the height at which the ray is incident on the medium, then you can see that the height h divided by z1 is essentially tangent of beta. So I'm looking at this triangle here. I'm looking at triangle Q. Let's call this point M. So I'm looking at triangle Q, M, and O. That's the origin. Right? I'm looking at triangle Q, M, O. The height MO is h, and the adjacent side is z1. So then we have tangent of beta is equal to h by z1. Or I could write z1 as h of tangent beta, or that is h of cotangent beta, right? So now then let's do a little more, right? So then I know that cotangent beta, right? Cotangent beta is nothing but cosine beta by sine beta, right? But cosine beta itself is square root of 1 minus sine square beta divided by sine beta, right? Therefore, I can write Z1. Again, we are trying to derive an expression for spherical aberration, but we are trying to start with a plane surface to begin with, and we are looking at the refraction from a plane surface. And we saw that a ray coming from point P at an angle alpha appears to come from a virtual image at Q, which is making an angle beta. This is because of Snell's law, right? And using simple geometry, we are able to derive that Z1 is equal to h times cotangent beta, which is square root of 1 minus sine square beta by sine beta, right? But we have a relationship between sine alpha and sine beta that is given to us by Snell's law. So I can write here sine alpha then as n2 by n1 sine beta. For simplicity, let's call this n2 by n1 as just n. Don't be confused, okay? Here only in this lecture, only for this lecture, instead of writing n2 by n1 every time, I'm just using n as n2 by n1, okay? So then I can write sine alpha is equal to n sine beta, right? And then I can use this to express z1 in terms of sine alpha, which should be straightforward, right? So then that would be equal to, so we had z1, remember it is negative z1 because it is on the left hand side, as h over sine beta square root of 1 minus sine square beta, and we saw that sine beta is equal to sine alpha over n from Snell's law. This is Snell's law. We just recasted n2 by n1 as n itself, correct? So then using this, I can write the same thing as h instead of sine beta I would get a sine alpha, but I would get n, right? And then under root 1 minus I would get sine square alpha by n square, right? Now therefore I can write z1 itself as negative because I can transfer this negative sign to the other side. So I can write z1 as minus nh by sine alpha square root of 1 minus sine square alpha by n square, right? Again, we are getting all this from the geometry of the system itself, right? So now if I look at sine alpha, this is alpha, sine alpha would be opposite side by a hypotenuse, right? Sine alpha would be opposite side is the height h. The hypotenuse is this, which would be simply a sum of this and this under square root. So I would have this as h square plus z0 square, right? So that is sine alpha. So I'm going to plug this in again back into the equation here for sine alpha. So we saw that sine alpha itself is equal to the height divided by h squared plus z0 square, right? So if I use this, then I can write z1 as minus, right, nh by sine alpha is this, so I can write h, and instead of writing this in the denominator, because sine alpha is in the denominator here, I'm going to just move it to the numerator, right? So I would have square root of h squared plus z0 square, right? And then here I would have 1 minus 1 over n square. I have sine square alpha, so sine square alpha would be h square by h square plus z0 square, and this is all under a square root, so I'm just going to express it as to the power half, right? So this is the expression that we have for sine alpha. So then what we could do further here is we can pull out an h squared as the common factor here, right? So I can do that by, so first let's cancel this, right? Then I would have minus n. If I pull out h squared here, then I would get another h here, but then here I would have 1 plus z0 by h0 both squared to the power half, right? Oh, sorry, I apologize. I'm not pulling out h. I would like to instead pull out. I made a mistake here. I apologize for that. So the h actually got cancelled here, so I'm pulling out z0. So if I pull out z0, I would have z0, right? Then this would be 1 plus h square by z0 square, right? And similarly here, if I were to write this 1 minus 1 over n square h square, even here if I pull out z0 square, I would have basically 1 plus h square by z0 square to the power minus 1, because that is in the denominator, to the whole of half. So we didn't do anything different. This is the mathematical expression that we got purely from geometry, and from here we substituted the value for sine alpha in here, and then we cancelled out the h's, and here I pulled out a term z0, and same thing here, I pulled out a term z0 as the common factor. And we are doing this because if you go back to the original diagram, z0 is where the object is, right? So our idea is to see how far I am from the object, right? How far I am off from the object. What is the difference between z0 and z1? That's how we are going to know how aberrated the image is. So we're trying to derive an expression for z1 in terms of z0. And z0 is something that we know because we're placing the object here. So if I know the distance and I know the refractive indices n1 and n2, I should be able to calculate what should be this z1, right? And once we know the expression for z1, then we can see in what ways can we correct this monochromatic aberration such that the image I see is basically the z1 is almost reduced to z0, that there is no aberration. That's our goal. So to that end, we're trying to derive an expression for z1 in terms of z0, and this is where we got. But as you can see, this is already a very complicated expression. So what we are going to do is we're going to do some approximations here, right? And to do that approximation, we are just going to use the binomial approximation. So we're going to write this as minus nz0. This is 1 plus. So if you have 1 plus x to the power, a fractional power, you can write it as 1 plus nx, right? That is the approximation. So using that approximation, I can write this as h squared by 2z0 square, right? And similarly here, I would write inside the here I would write 1 minus h square by n square z0 square, and this term we will come to this term, but there is a power half here, so I'm going to put 2 here, right? And from here for the second term, right, that is this term, both h square and z0 square are squared, so, and it is in the denominator, So if we multiply it with h square again, we will basically be getting something like h to the power 4. And so if in the approximation that h by z0 is much less than 1, we can essentially ignore this term. So we are making an approximation that if h by z0 is much less than 1, we are ignoring this term. Obviously, as you can see, this is not going to give you the exact answer, but nevertheless it's an approximation. So we are trying to get an approximate expression. So this would be the approximate expression for z1 in terms of z0. So this we derived for a plane refracting surface while studying monochromatic aberration, right? So now we have an expression for Z1. We know Z0, so then we can calculate the aberration, which is the delta Z, which is the difference, right? So the difference, right, would be essentially equal to, so we have a Z1 as minus nz0 1 plus h squared by 2z0 squared 1 minus h squared by 2n squared 0 squared. This is the expression that we derived. Once again, this is an approximate expression, right? So if I go ahead and do the multiplication and again ignore the higher order terms, right? So if I do this, we have 1 times 1 is 1. 1 times minus this is h squared by 2n squared z0 squared, right? This is again I have h squared by 2z0 squared. Then when I multiply this with that, I get minus h to the power 4, 4n squared z0 to the power 4. Like I said, we are going to ignore this higher order terms, right? So if I ignore this this higher order term, then I can write this as minus nz0 1 minus. So here I can take out h squared by 2z0 squared as a common factor. Then I would have 1 minus 1 over n squared, right? Or I can write this further. Again, this is an approximation because we're ignoring higher order terms. So minus nz0 1 minus h squared. I'm going to pull this n squared right out, so I would have 2n squared z0 squared, and here I would have n squared minus 1, right? So this is the expression for z1, right? So then so you have you have, this is z0 1 minus something, right? So this extra term that you're seeing is what we call as the aberration. So you can express aberration then delta z as this extra term, which is minus h squared by 2n squared z0 square n square minus 1, right? But also remember that we had an n here, so when we are actually multiplying, we need to multiply even this factor with an n. So here we would not get a square, we would simply get h squared by 2n by z square. So this is the expression for aberration, and in fact this is the expression for longitudinal, because we are looking along the axis, right? This is the longitudinal aberration. Remember that we looked at two different measures for aberration. One is longitudinal along the axis, another is along the screen that is placed at the paraxial focal point, which we called as the lateral aberration. So what we derived is an expression for longitudinal aberration, right? And here we considered a plane refracting surface. So a plane refracting surface has a radius of curvature that goes to infinity, right? So you don't see any terms that have to do with the radius of curvature in the aberration. But what we truly want to do is we would like to derive an expression for aberration, for longitudinal aberration for a spherical surface, because lenses are made up of spherical surfaces. But that becomes extremely cumbersome and very complicated. But you can go through the same process, and essentially the delta z that you get looks something like this. Looks like n2 minus n1 by 2n2 1 over z0 plus n2 minus n1 by n1r whole square 1 over r plus 1 over z0 whole square multiplied by n2 plus n1 by n10 plus 1 over r times h squared. Easy enough, right? So this is the aberration for this is the aberration. This is the true spherical longitudinal aberration. I'm not expecting you to remember this equation or anything. I'm just showing you how we can derive it, right? So that we know that basically the spherical aberration depends upon the radii of curvature, right? So here r is the radius of the curvature. So based on the radius of curvature, you should be able to see how spherical aberration is coming along, right? It's exactly the same procedure. We started with a plane surface, right? Plane refracting surface, and we went with a ray that got refracted, and we drew it back, and then we tried to calculate this difference. So instead of having a plane surface, you could derive the expression for spherical aberration by using a spherical surface, right, like this. And that's where you would get this expression. So the reason I would like to show you this expression is that I want you to realize that the aberration depends upon the radius of curvature. It also depends upon the refractive index, right? It also depends upon z0, which is the object distance, where you place the object. But once we have a lens, the property of the lens is basically the refractive index is for the lens. The radius of the curvature is a property of the lens. So then I can change the properties of lens to accommodate this monochromatic aberration. And how do I do that? By adjusting the radius of curvature. Here this is spherical longitudinal aberration again for a spherical surface, for one spherical surface. If you have a lens, you would have you would have two spherical surfaces, right? So you would have two different radii of curvature. So we can define a new quantity, right? It is called the shape factor. I want you to remember what shape factor means. Shape factor is in general denoted by Q. It is for a lens, it is given by R2 plus R1 divided by R2 minus R1. So you can change the radii of curvature in a lens. So if I have a lens, I can change the radii of curvature R1 and R2, and by changing this, right, I can get different shapes. For example, if R1, right, is equal to R2, then Q basically goes to infinity, right? If R1 is equal to R2, Q basically is undefined. That is, if you have both surfaces to have the same radii of curvature, right? If let's say if R1 is equal to 2R2, right? Then you could see what would be the shape factor. The shape factor would be 2R2, sorry, R2 plus 2R2, right? R2 minus 2R2. Right? So that would be 3R2 minus R2. So that would be negative 3. for example, right? It's a dimensionless quantity. Or if I make it half, if R1 is equal to half of R2, then I can write Q as so R2 would be equal to twice as much as R1. Then I would have Q is equal to 2R1 plus R1 divided by 2R1 minus R1. So that would be equal to 3R1 by R1, or it is plus 3, right? So in that sense, basically, when Q is positive, right? When Q is positive, that means R2 is necessarily greater than R1, right? When Q is implies Q is greater than 0. R2 is less than R1 implies the shape factor is less than 0. So why do we need the shape factor? It is because once we know the shape factor, we can it is called bending the lens. If you're looking for this optics jargon, this is called bending the lens. That is, by changing the shape factor, by changing the radius of curvature, you're changing the shape factor, or you're adjusting the shape of the lens, or it is called bending the lens to get rid of the aberration, right? So you can do this by bending the lens, by adjusting this, and um, if you do the math of the complicated expression that I showed you on the previous slide for spherical aberration, if you do the actual complicated math, um, uh, you can see that for some values of Q, you would get basically a very low aberration. So in other words, you can plot this delta Z, right, as a function of Q. So this delta Z is for one spherical surface. So if you have a lens as such, the lens would have a longitudinal aberration of basically that looks something like, in case of a lens, the longitudinal aberration is given as S, that looks as n minus 1, the focal length square, divided by the height square by 2n square by 1 over r1 cube minus 1 over r2 minus n plus 1 by f 1 over r2. This is the expression of aberration for a lens. Again, I'm not expecting you to remember this expression. My idea in discussing this is to show you that these expressions could be derived, although they are cumbersome. Like how we derived the expression for a plane surface, the expressions for spherical and lenses could also be derived. And here you see that you have both R1 and R2 because it's a lens. You have two spherical surfaces in a lens. And we also defined a shape factor Q, which is R1 plus R2 divided by R1 minus R2. So you can recast this S in terms of Q, and then you could plot the spherical aberration, right, the spherical aberration as a function of Q, and see where this would be the minimum. Or you could even do something like set this to 0 and figure out what should be the Q factor, the shape factor, to have minimal aberration, right? So that's how we deal with aberrations in monochromatic light. There is another kind of aberration that is called coma, which we will discuss in the next lecture. So far, we have only discussed aberrations on the axial points. That means that I have always been talking about an object is along the axis, right? Even when we talked about polychromatic aberration, we still considered that the object was on the axis. Now, what happens if the object is not on the axis? What happens if the object is actually here? It's off axis. It's off axis. Then that leads to another kind of aberration, which is called chromatic chromatic aberration, or it is simply called coma. So off-axis points lead to coma or chromatic aberration. We're not going to discuss that in detail now, but we'll discuss chromatic aberration soon. And with that, we should be done with geometric optics. And then I would like to start with the wave equation. And to do this, I request that um, you revise what is an electric field, right? What is a magnetic field, right? Your basic E&M course, wherever you have taken it, and read about what electric field is, what magnetic field is, and if you have already seen, I would like you to read what Maxwell's equations are. You should already know this because this is actually a prereq for this course, that you know electric and magnetic fields. Even if you don't know, I will try to summarize them, but I'm only going to summarize them in the interest of time. But if you truly want to understand, you can study what these electric and magnetic fields are, and I would advise that you go back to whichever textbook you studied from, electricity and magnetism, and reread those things like Gauss's law, what is magnetic field, and what Maxwell's equations are, and then we will come back to this bring this electric and magnetic field back to our optics course. And from here, my idea is we will use Maxwell's equation, we will derive the so-called wave equation for light, we will see how the speed of light comes from the wave equation, and after that I want to talk about things like Michelson-Morley experiment, trying to find a medium for light. And then I would like to touch upon what is special relativity, Einstein's theory of relativity and what it has to say. And then I also would like to touch mainly about the quantum theory of light. I would like to talk about in specific what we call as second quantization. Right? Second quantization means you're treating waves as if they are particles. First quantization means you're treating particles as if they are waves. For example, if you have an electron, you could say, oh, this electron behaves like a wave. And that is first quantization. Second quantization is you have a wave, but it appears to behave like a particle. Right? So I would like to discuss second quantization, and my goal is that by the end of this course, I want you to realize what a photon means, because it's very widely misused even by even by people who are doing photonics, for example. So photon is a virtual particle that is in second quantization when we are treating uh, a classical wave of electromagnetic wave as if it's made up of these virtual particles of quanta. So I would like to make the distinction between virtual particles and real particles, and give you little insights into quantum electrodynamics before we finish the course. But right now we have set the stage. To give you a historic perspective, we are somewhere little bit after Newton and a little bit before Maxwell. So we are in 16th, 17th century right now as far as optics is concerned, whatever we discussed. And we can now move towards understanding light. Right. We actually, so far we have not really talked about what light is. We were just looking at how to manipulate it with lenses and mirrors, and how it behaves. But we still have not asked the question, what is it actually? And that is where we are progressing to give you an idea. Okay, so with that, I will close this lecture, and um, I know that the exam, there were some issues there, so that some of you emailed me. I will circle back to you and update the grades on Canvas, but please do brush up your E&M. Thank you.